Before we begin, allow me to take a few moments to introduce NASNI, the National Astronomy Network of IAPT. NASNI is a dedicated platform under the Indian Association of Physics Teachers designed to foster interest and engagement in astronomy and sky watching among students, educators, and general public. Why was NASNI created? NASNI was created to bridge the gap between new sky gauges and experts by providing observational guidance in astronomy and astrophysics. It aims to nurture curiosity, promote a scientific temper, and connect enthusiasts with leading astronomers, astrophysicists, and experienced sky watchers. How does NASNI operates? So it organizes workshops, lectures, and observational sessions for beginners and enthusiasts, facilitate interactions with professional astronomers from different planetariums, research institutions, and academia. It encourages community participation through sky watching camps, online discussions, and field observations. It also supports schools and colleges students in astronomy projects, competition, and research endeavors. In the coming 6 months, NASNI has an exciting agenda. It plans to conduct both introductory and advanced courses on sky gauging and telescope handling, organize a national level observational challenge, set up regional astronomy clubs to strengthen grassroots participations, and host a public lecture series featuring prominent astrophysicists and science communicators. How will people benefit from NASNI? Through these efforts, NASNI envisions creating a vibrant ecosystem where individuals can gain hands-on experience, they interact with experts, access structured learning paths, and contribute meaningfully to citizen science and real astronomical research. Now, how does NASNI wish to grow in future? So looking ahead, NASNI aims to expand its reach by establishing local astronomy hubs in schools and colleges and developing mentorship programs, making partnerships with planetariums, research institutes, and observatories. It also developed a mentorship program connecting young sky gazers with experienced professionals and promoting collaborative amateur projects that can lead to scientific discoveries. Now, continuing this mission of outreach and engagements, IAPT, NASNI, organizes talks aimed at building a strong national community of astronomy learners and enthusiasts. Following that tradition, today's event has been organized to continue this effort, and we are grateful to have such an engaging session lined up for all of us. Today's session features a special talk by Professor Humchand, who is also my PhD supervisor, a well-known astrophysicist whose work has inspired many young researchers like us. We are honored to have him with us today. So I formally introduce Professor Humchand and begin the talk now. I will invite Mr. Prayag to take the stage and introduce Professor Humchand to the participants. Thank you so much.
Hello, so am I audible and visible as well?
You are audible.
Okay, so hello, my name is Prayag Sharma, a PhD student working under the guidance of Professor Humchand. It's my distinct honor to introduce our esteemed speaker today, Professor Humchand. Professor Humchand is a leading astrophysicist and currently serves as a professor in the Department of Physics and Astronomical Sciences at Central University of Himachal Pradesh. He earned his PhD from the Inter-University Center for Astronomy and Astrophysics, IUCA, and was awarded the prestigious Peter Gruber Fellowship Award, which took him to the Institute of Astrophysics in Paris. He has been actively involved in several major astronomical collaborations. Notably, he is a member of the Instrument Science Development Team of the 30-meter class telescope and contributes to the Castor and INSIST space missions. He also led the India's participation in the 4-meter island telescope project and is currently working with ISRO to set up a 1-meter class telescope here in Himachal Pradesh. Professor Chand's contributions have been widely recognized with honors including the Peter Gruber Fellowship, CSIR JRF, R.K. Bhalal Award, Young Associate of the Indian Academy of Sciences, and India Top Cited Paper Award. Beyond research, he is a dedicated mentor and science communicator, having guided numerous PhD students and led various outreach initiatives to promote astrophysics in the broader community. Today, he will speak on Stardust and Us, the life cycle of stars, and the evolution of humans. I'm sure his talk will be both enlightening and inspiring. Please join me in welcoming Professor Humchand.
Thanks a lot, Prag and Ritesh. Thanks a lot, Hemant sir. So I hope I'm audible and my first slide is visible.
You are audible, sir, and slide is also visible.
And they are changing also, right?
Yes, sir. Yes, thank you.
Okay. So it's it's a great opportunity which NASNI is giving to us. So it's really wonderful effort Professor Hemant and Professor Pikyarwale sir is doing, especially for our astronomical community. So I hope I will try to make justice with this opportunity. Today, what I'm going to talk about is I'm going to link human evolutions with the star and how we are linked with this vast universe. So that's the title, Stardust and Us. To set the stage, so we can see as a human being in these pictures. And you see various components, what we have, what our body and other stuff, whatever we are using. So my goal in this talk is going to be that how we as a human being, as a body, are linked with this cosmos. So if we try to see as far as material is concerned, so it is this periodic tables which we have, which constitutes all the material world, whatever we are. My goal is to convince you that there is a great linkage between us and all these stars, whether they are small star or large star. So this is going to be the goal. This is going to be the message which we are going to study. So question is like, what connect this our life, which especially life of star, to the human existence. You might have heard about this quote by famous Carl Sagan, that we are made of star stuff. So this is something which I'm going to convince you that this is indeed true. So the way generally somebody can answer it is like the element which make up our body, carbon, oxygen, iron, and calcium, they are only forming the core of the stars. And when massive supernova explosion happen, these elements get scattered in the space, and these cosmic debris form new stars, and then planet, and then on those planets we are here as a life. Right? For example, sun is a kind of second generation or third generation star. So in that sense, I'm going to convince you that part of the star is literally what we have. So we are literally the universe made of a consciousness, apart from these materials. So this is the kind of journey which I'm going to take you, and I'm going to convince you as a physicist, like whatever statement I have made, how they looks very plausible to you, and what are the journey which we have taken for this. So I will start from here, little bit just introducing you. This is our solar system, and you know all this story that we have sun, there is equator, there is a tilt which is responsible for winter and summers, because Earth is moving around the sun. So all this story we know, and we have moon. So all these things are very interesting, very exciting, and people start asking these questions. And when they start asking these questions, slowly and slowly this field grows. So if I just try to take a kind of a small analogy, apart from summer, so summer and winter or season, whatever we have, let me talk about a little bit about the distances. Okay, just to make set up the platform. So that if I try to take radius of the sun and radius of Earth, they're almost 100 times. And if they're 100 times, then the volume is going to be millions times, right? 10 to the power 6 times. So that means we are going to have something like a few lakhs legs of Earth, dozens of legs of Earth inside the interior of the sun. So that's the going to the comparative size of sun and Earth. Like as far as distance is concerned, so this light travel time between sun and moon, you can take something like few seconds, 1.25 seconds, and between sun and Earth, something like 500 seconds. So this is the kind of comparison which we have. And if I just try, like, we want to have a feeling for it. So from this slide, you can take this message. For example, if I just take Mercury as a peppercorn, then Saturn is going to be something like large grapefruits, and Jupiter is going to be something like watermelons, and Earth is going to be something like cherry tomato size. And as far as sun is concerned, sun is going to be something like, here you are going to put something like 12 or dozens of lakhs of Earth inside it. So sun is going to be very, very large in comparison to that, right? So now if I just want to tell you in brief that how these stars are formed. Let me just try to take you through that by this slide. So you can focus on the first part of this image. So what I'm showing here, there is a gas clouds. And those gas clouds are quite large. So if there's gravitational instability, what do you expect that if somewhere density becomes larger, it will start becoming larger and larger under the influence of gravitational pull. And what is interesting here, when I go from this top left to top middle one, I'm showing you a structure which is not now a small sphere. That bigger sphere has become a small sphere, but it is something like a this kind of thing with bulge in the center. So this we also understood as a physicist, when it can, when this such kind of situation can happen. So it is happening because if we have angular momentum in the gas, by which we are going to start making the cloud, then what happened? The gas from the polar axis will fall freely, but there is going to be a resistance force, like in the disk axis, because of centrifugal force. So slowly and slowly, the smaller structure is going to form like a disk. And if you go in the third pictures here, then the inner core is going to become much hotter. And if it's going to become hotter and hotter, and then it also is going to clear the region by evaporating the region nearby. And then you go in the down third, in the lower panel, left corners. So you start seeing as time passes that there is going to be a compact object, there's going to be a dense club object in the center. And there is also going to be some ring kind of structure depending upon the angular momentums. And they also might grow in instability and try to clear their path by pulling it. So, and it's going to be a formation of later on in the last figure. You might look like a compact, a solidified object which has cleared its path, which we call planets. So this is in brief a message which you can take from this slide, that this is the kind of understanding which now astronomer has how solar system might have formed, and there are evidences for that, because all these planets, whatever we have in solar system, should be on a coplanar, and which has been verified observationally. Okay. And now let's come to the central part, which I'm going to introduce you as Sun before we start answering this question, whatever we are starting in the beginning of the talks. So I'll just make a zoom on versions here in the right side. Okay. So if you try to see it, it's going to be a huge gas clouds. It's going to be hot, and there's going to be temperature gradient from the surface toward the core. In the core, temperature has been shown here. It is something like 16 million degree kelvins. And so things here become a little bit where physics is going to be very important. For instance, I can try to give you, if temperature is so high, what kind of physics and physical phenomena we need to worry. If the photon is generated here by any means, so how it's going to transfer from the center to the surface, all those kind of rich physics is this astronomy and astrophysics offer to the physics student. For instance, I'm just saying here, if I try to take this radius of the sun, it is something like 2 light seconds. It's not very large, but the actual time a photon required to travel from the center to the surface is something like 30,000 years. So there is going to be a lot of absorption, emissions. So in fact, those photons which was originally generated in the interior of the sun got modified when they leaves. So we in physics commonly know that that means there is a continuum spectrum which we call black body spectrum. Okay, so rich physics, a lot of variety and huge dynamic scales which one can do here. So maybe we will not go today on details. So this is just a brush up. So now what is happening in the interior at this stage? Okay, this is a message which you can take from these slides, which I'm showing here. So what you see here, if temperature is in million degrees centigrade, what might happen, you might fuse hydrogen into heliums, and then because of mass defect and mass getting converted into energy by E equal to delta M into C square. So we can generate energy. And this is what is possible only in the interior of the star, because required temperature is going to be million degrees centigrade, which we cannot create otherwise. So this is now, I am now going to bring you towards that how this element which we are creating here, that hydrogen we have converted into helium. That means if you need helium, you need a temperature which only star interior can provide. You can do the calculations, and again a rich physics here, again nuclear reaction, all those kind of physics. It turned out to be 10 to minus 15 calories, very small in one reactions. But even in the sun, we are having in the interior 10 to the power 38 such reaction per second. And even if you are consuming 10 to the power 38 hydrogen per second, then we have something like 10 to the power 56 hydrogen in the sun, which we can burn, and we can sustain this reaction for millions of years. And as a result, sun can keep shining for millions of years. So this is what is happening in the sun. So I'm not going right now in the history that how did we understand, how did we know that this is the mechanisms finally, which is happening in the interior of the sun. So right now I'm just giving that what is the theory, but many alternative was proposed. So this is the theory which is actually confirmed by observations. So now you might ask that, okay, well, we are happy that sun is shining and it is giving us everything, lot of radiations. So life as well. So what will happen? Will it continue forever or not? So it won't continue forever. So when it finishes its hydrogen burning in the interiors, so then what we are going to have is some something called a post-main sequence kind of event. So what is that? So right now, if I just try to ask that if sun is emitting an energy L dE by dt per second, so what it is going to be? It's going to be 4 pi r square, which is surface area, into sigma T to the power 4 effective temperatures. And if I have this is called luminosity, whatever I have written in the first one, and whatever we have written in the second is called effective temperature multiplied by surface area. So now I have drawn here a diagrams. In the x-axis there is a temperature, and y-axis it's a luminosity. In astronomical jargon we call it absolute magnitude, but it is basically luminosity in the increasing orders. So I am saying sun is all these stars. Sun is somewhere here. What I'm expect from here, that luminosity and temperature should follow a relationship. If I take R as some values of R, let's say, for example, for the case of sun. And when sun is going to finish, when sun is burning, so sun is going to stay in this phase where sun is marked here in these diagrams. So it will stay here for a quite long times. And this is our expectations that we should have in the log L and log T plot. This is the logarithmic of luminosity, and this is logarithmic scales here. So we should have a kind of this kind of lines, what I'm showing also in the right side here, vertical lines. So stars should actually stay most of the time within these regions, this shaded region. This is famously called HR diagrams. I'm just bringing it a little bit here for your discussion, that what actually how star evolves, just to bring that discussion in. For instance, if I ask you that we might have heard about this twinkle twinkle little star, for example. So we have this kind of picture in the sky where we have put color coded the star also. Some stars are hot, some stars are cold. And blue star are called hotter star, and red star are called colder star. So just to understand it, just to give a glimpse of that, let's come to this middle picture here, middle diagrams here. So in the x-axis, we have wavelength here. In y-axis, we have intensity here. So now if I just try to show you here, it's a black body curves, and we can do observation in visible and different band, right? Just to measure the flux at different band. It could be, let's say, blue, then it can be greens, and we can take different, this is called colors, right? So astronomer has measured this color. It's very easy to measure. Even small telescopes are enough. People, even amateur astronomer, can also afford small filter, blue filter and green filters or yellow filter. And they can measure this color. And this in the x-axis is the color difference, that measurement of flux in one band minus measurement of flux in one other band, which is actually a slope of these curves, right? Which depend upon the slope of these curves. And very interestingly, if you see in the y-axis, the luminosity again in logarithmic scale. So these dots are the real position of the star, whatever we measure in the sky. So this is a kind of very very interesting plot in when people start studying this stellar evolution, that how stars grow. So one star doesn't know another star, right? They are independent. So why all of them should get clustered in this small narrow strip, which we call main sequence. So that means there is a very tight relationship between these two quantities, whatever we have plotted here. So color is measure of temperature in the black body, as we know from the physics. And y-axis, which we call absolute magnitude, is a measure of luminosity. So this is what I was just trying to show you in the previous slides, that this is what we are actually expecting, that there should be some relationship between luminosity and temperature. but assuming R to be constant. But R is also varying, it depends upon the mass. So it is a very interesting physics problem that if I give you mass, if I give you radius of a star, so, or if I give you mass of a star, what radius it will be settled down. Okay, in fact, our famous Nobel laureate Chandrasekhar has also done great work on this kind of mass and radius relationship. We will. So then we can predict that there is a lot of physics here, and almost most of the A's stars stay here in the thermodynamical equilibriums, in hydrostatical equilibriums. But what happens when a star finishes its fission or fusion reaction, that is hydrogen is finished. So then what happens? That's become very, very interesting. So I am showing you diagrams here. What happened after post main sequence? Let's take example of sun. Example of sun is somewhere here in these diagrams. In the x-axis the temperature, y-axis is the magnitudes or luminosity. Sun is going to leave this main sequence and it will become subgent, and then it will become a red zent. Okay, the size of red zent is going to be something like when sun is going to expand, almost it's going to engulf Mercury, Venus, Earth, and it almost will reach up to Jupiter's. So when sun is going to leave this main sequence, and what happened in this stage, in the main sequence, hydrogen was burning and getting converted into heliums. But in subgent phase, helium burning also starts. And then this red zent phase comes, and after residence, it actually throughout the outer shell, it becomes a planetary nebula. And whatever is left in the interior is going to be a compact core, which we call white dwarf. So this somehow in this diagram lies somewhere here. So ultimate fate of the sun is going to be like a white dwarf. White dwarf means they are not very compact stuff. If you just take analogy that if you take a spoons of white dwarf, so you probably need a kind of JCB or kind of a few tons of weight to lift it up. And this is going to the situation in the white dwarf. This is in the right side, it is the image of the sky. And if some star become red zent, the luminosity becomes very large, although temperature is small because size become very large. And analogy is given here that this is going to the size of a star, whatever is shown here. And in comparison to Earth, it's going to be almost 5 to 6 times larger, Sun-Earth distance. And if you take Jupiter orbit, it's almost going to be twice than that of Jupiter orbit. So that means it's also going to be completely engulf the Jupiter at rest. So this is what happened for sunlight star, like whose mass is up to 1 solar mass. So you might also ask what happened if mass is much bigger. So if mass is something like 8 to 10 solar mass star, which was actually in the main sequence. So then what happened? Because mass is very large, after hydrogen burning, helium burning start, and after helium burning, carbon burning start. After carbon burning, oxygen burning start, and after that, neon fusion start, magnesium fusion start, silicon fusion start, and so in the interior temperature become larger, so heavy nuclear fusion start. So outer shell, lesser heavy nuclear starts. So then it becomes like an onion kind of structure that in the interior, in the end, you are going to have iron. Then outside that is going to be silicon. Then outside that's going to be magnesium, then neon, then oxygen, then carbon and helium. And hydrogen burning is going to start in the outer shell because temperature is going to be enough even there for hydrogen burning. So this is was my goal to tell you this story now. That now I'm going to cook almost all your periodic table in the interior of the star. But here is a catch here. Now you will ask me, because most of you are from the physics background, that this fusion will not happen beyond iron because iron is the most stable nuclei. because binding energy beyond iron is going to be smaller than iron. So you can't have exothermic reaction, which happens spontaneously. So then what about the much heavier elements? So much heavier element will also produce after this stage what using by supernova explosion. So what I mean by that let me just give you a pictorial picture first, that if star is small mass star, then first it's because of gravitational collapse, it's going to form a proto disk. In the center, there's going to be star. And then if there is an angular momentum, there's going to be small gravitationally bound structure like planets, which might also become solar system. It consists also when hydrogen burnings happen like yellow kind of star like suns. And when burning finishes, helium burning start, then it could also turn out to be red giant. And finally a planetary nebula. And when it's through the final outer shell, it becomes a white dwarf. This is the fate of star up to 1 solar mass. If mass is much larger, then things become much quicker because fusion reaction happen at much faster rate. You mostly have blue star and then red supergiant. And in the interior, then what happens? When there's nothing to burn, then there is a sudden collapse in the inner shells. And then there's a rebounds, which we call a supernova. And these ejecta of supernova can even go in supersonic speeds. And if you have very large mass black holes, then there's going to be a remnant which will go out. And in those remnant which goes out, which I call supernova, there's going to be shock waves. And those are the shock waves which try to combine massive element to form much massive element like irons, like silver, gold, etc., titanium, nickel, zinc, coppers. All these are formed in this supernova explosion on those shocks, which are well studied. And then the interior will be either black hole, which we don't know what is the fate of that matters, or it could be neutron star, which is supported by neutron degeneration, like white dwarf is supported by electron degenerations. Right? So this cycle goes like this. This cycle goes like this. Low mass star end up in a white dwarf, and high mass star will end up in a big explosion. So now I'm linking it to you with that. Let us remind us about our theme. Our theme was we are going to link this our life element which we have with the life cycle of star. So I'm now very close to that if you pay attention. So what I'm telling here that all these elements have been cooked in the interior of the stars, and the supernova's explosion are the one which shatter the star apart from the core and throw this material out. Otherwise, all this material that was cooked in the star would have been locked inside the star. But because of the supernova, they are thrown out. It happened mostly only in the outer shells. So how do we know that? Okay, how do we know that in the context of our solar system? So now let me tell you a little bit, just remind you that we have a fingerprint of atom in the form of transitions. So what I have shown here is atomic transition for hydrogens, very simplest atom, N1, N2, N3, N4, different stages. And then there are three possibilities. One possibility is called emission, okay, emissions. You take this line here where I put a mouse here, this green one. If electron is jumping from N3 to N1 state, so the energy level difference between energy third and first state, that is the ground state, delta E is going to be H nu, photon will be emitted. This we know. And in absorption, opposite will happen. The photon come, it take electron to the N equal to 2 to let's say N equal to 4 state, and then photon will be used, but then it will be emitted in random direction. That for you it is a loss, so we call it absorption, right? And there could be ionization when from ground state goes to very high stuff. So this line theory we know that's very well from atomic physics. Especially in hydrogen, there is a very interesting line which we call hydrogen hyperfine structure line. This 21 centimeter lines. Nuclear spin could be parallel or they could be anti-parallels. right? Electron spin and nuclear spin, they could be parallel or they could be anti-parallel. And there's an energy difference between the two states. And the flipping can happen if you go from high energy state to low energy state. A photon will be released, and that photon has a wavelength of 21 centimeters, which falling radio. It's very interesting for many cosmology kind of implications or something exotic kind, dark matter kind of stuff, which I'm going to introduce you also, if time permit. Well, so now I have a star. Let's say I'm just taking an example of sun. So if sun is emitting a photon and there's an atmosphere, and this atmosphere is nothing, it's the material by which solar system was formed. And now if a photon is coming from the hotter sun surface, and it is coming toward us, and then there could be absorption lines because of this atmosphere of the sun, that photosphere of the sun. There is a layers of gas, they will cause absorption line. And these absorption lines are fingerprint of atoms, and we can identify them uniquely. And this is what the solar spectrum look like. Right? Now, I am there almost. What I have actually taken to you, that material was cooked. I told you that it might have been thrown out because of supernova. And then I just took a spectrum of the sun, and from the atmosphere of sun, that is the atmosphere of a star, I can try to see what are the kind of material which has been used to form the star. So that is the example of sun. So now this is the theory now. So I have a star which is made, this is a sun, made by materials. And that material I can now understand by taking the spectra of the sun, shows a lot of lines of various atoms. But I know that those atoms of different high mass atoms, other than hydrogen, will be only and only cooked in the interior of the star, especially high mass star. So that means, since I have seen them here in the solar system, that means the material by which my solar system was formed constitutes of stardust, which is a mixture of many, many hundreds and thousands of supernova. That stardust has heavy elements. Although hydrogen is most abundant, but there is also heavy element. Heavy element can only be there if those elements have come out of the star core in the form of supernova. This means the material by which sun is formed or our solar system is formed is a stardust of many, many dying stars. So now in this diagram, left side, this is supernova which has exploded. It has thrown the material in the interstellar medium. And we know that material by which solar system is formed is a second generation or third generation material, which is reprocessed material. Reprocessed material means many, many supernova and dying star has contributed to this materials. And now we are on one of this planet here, which we call Earth, around the sun. That means the material by which Earth is made is a stardust material. And if that is the case, then what we are made of is made of the material from the Earth. That is, we are also made of the stardust material. And the stardust could be thousands of stars which has been dyed, and that has contributed for all this material what you have. You might have gold, you might have titanium, you might have this carbon, you might have this silicate, you have this whole periodic tables, and even your body. And you might have hairs, you might have proteins, and number of stuff in whatever in your bodies have. It is really this periodic tables. And periodic tables mean up to irons. It has been cooked in the interior of the star and then thrown out in the form of supernova. And heavy elements has been cooked in the supernova shock waves. So this is what we are consuming from this Mother Earth by a lot of agriculture products, lot of plants, or any other materials. So you might even try to think yourself now that you might have two here, which might be belonging to two different supernova. and sitting at a distance which is very, very high, because I give you analogy of 1.5 second for moon, 500 second for sun, and it may be 10,000 times the nearest star. It may be millions and millions of times to the other star which has contributed. So our body, in the essence, or any part, any physical structure which we see on the earth, is linked to hundreds and thousands of stars, dying star, that is supernova, which might have existed in the universe. So such a connectedness we have with the universe. So partly I have answered the question which I have asked right in the beginning about our connectedness. Okay, how we are as a human being linked to the stardust. I'm just giving you a little bit analogy here for you, just to do some homework, like how big and how tiny we are as a planet Earth in this whole business. For instance, if you take one image, this is an image of a Cassiopeia, one of the stars. It is taken in the calcium. Basically, whatever emission is there, it is proportional to the amount of calcium. So similarly, we have its image in optical band. This is in calcium filter. This is in X-ray. And small exercise has been done here. Mass of Cassiopeia is 20 times sun. Calcium is even 1/20th of a 1%, 0.05%. And I have asked a question: can you link even this 0.05% with the whole amount of calcium which you can produce on Earth? So just for a funny exercise, assignment is given. How many kilogram calcium is in this supernova remnant Cassiopeia? And can you translate it to how many milk of glass? And if you want to produce them, so many milk of glass, how many cow we need? So it turned out that we need something like 10 to the power 31 glasses of milk just to produce that 0.05% biomass calcium present in this Cassiopeia, 10 to the power 31 glasses. So even if we have something like 125 cow, which is giving 6 to 7 liters of milk, right, per day, even if you have 125 crores of cow, that is every Indian has one cow. So we need 10 to 19 years to milk them to produce such a 0.05% of the calcium present in single supernova remnant called Cassiopeia. And our life is something like 10 to the 9 year till now, whole universe life. You can imagine 10 order of magnitude. This is just about one star. We are just talking about. You can do this for a small exercise. And if you just want to get some idea about that, how big we are, I can just walk you through a little bit here. Maybe for 10 to 15 minutes, 10 minutes or so. But so that I can also keep some time for question and answer. Okay. So probably I'm feeling that you also would like to have an idea that what we know about universe, how big it is, and how do we know it. So try to imagine whenever you think about astronomy in relative terms. Okay, for example, you know, sun and moon, Earth and moon distance, you have idea about it, but 400 times is bigger the distance between Earth and sun. And we know these distances, then also we know these distances, whatever I have plotted here, different planets. We should start asking that how this thing has been done by the astronomers and whoever have done it. I'm just giving examples here. For example, Venus. You take sun here, Earth here. So I'm giving you a geometry here. You try to find an angle between Venus and Earth, sun over the year. So there is going to be only one point which I have written here as a right angle triangle when this angle is maximum. Otherwise, it's going to be smaller than that. But you know that angle when it's maximum, then you can use this trigonometry. If you know sun and Earth distance, you can find Venus distance. This is just an example. You can do it observationally. You just need to measure the angle between sun and Venus throughout the year. Only once, in fact, twice it will happen. That angle is going to be maximum, either in the left side or you can similarly have in the right side. in this orbit. So it gives you idea that how, or you can, for example, use then Kepler law and n number of things, different various observational techniques. And then we have a different method, parallax method, for example, for nearby stars, and so on and so forth, right? Because distance is a very important quantity. So we can try to see the shift in the star position in the sky is going to be proportional to their distances. And then we have distance measured as a professional astronomer at different times. Right? We call distance ladder. Second method depend upon the first, third depend upon the second, so on and so forth. We made a distance ladder. So as I said, we can go even to millions and billions of light years away. We can measure the distance. And things are quite, I'm going to probably disappoint you that we are too tiny and we are too small, and we just like one dust in such a big universe. This is what the kind of feeling which we are going to have. For example, if you take sun in 10 light year time scale, this is going to the pictures. And if I just take in 100,000 light year time scale, then almost sun disappear, and every point here is a star. And so we are losing our identity in this. And if I just take full galaxy and see here, there's nothing about sun, nothing special about the sun, nothing special about its location, nothing special about its brightness. And we have such a beautiful emerging picture thanks to the technology and telescopes that we have now this kind of picture. Not only this kind of picture, we have even gone much ahead in our understanding of the universe. But it's a lot of hard work. I'm just giving you an example how it goes when it was, let's say, in the 16th century or 17th century. People try to ask this question whether Milky Way is a spherical or it's not non-spherical. They use small telescope. Small telescope means smaller area accessible. Bigger telescope, bigger high distance accessible. And now they just did the counting of stars, how many stars they can count. You see, if it's spherical distribution, then we have one kind of expectation. If it's not spherical distribution, then in one side there's going to be increase with the aperture size of the telescope, in other side is not going to increase. And people, even just using small telescope, discover that we are not in a spherical, stars are not distributed spherically, but they are in a disc kind of shapes. Fantastic exercise. But they were wrong. But in this picture, they were thinking sun is in the center of the Milky Way, but it was not the case. And size of Milky Way was thought to be something like 30 kiloparsecs, but that was also wrong. But actual picture was something like this. We were not in the center. We were somewhere here, and sun was somewhere here. But we were actually, it was a limitation that we were only able to see this star. It was something called, because of dust, etc., we were not able to see further of a star. But this was a picture painted because of the globular cluster, whose distance we can find out. They were distributed not about the sun as a center, but center was somewhere else, which we call center of the Milky Way. And this was a lot of effort, a lot of hit and trials, and ultimately we end up in this kind of beautiful picture. Thanks to this technology, what we see in the sky by night is something like this. What actually it is something like this by mosaicing a lot of images taken at different time of the years. And now I'm just showing this slide to you. And this person has told that we are not alone. There are other galaxies as well. So we should not be very proud. So every dot here is a galaxy. And if I just go to the 1 million light year time scale, Milky Way almost disappear in this cluster. And if I just try to see different kind of beautiful galaxy, right? But again, puzzle, we can count all those galaxies. And then what we need, that is something only 5% of the total mass. And if the evidences for this is given by this something called this hydrogen rotation curve in the Milky Way. So what we expect is these dotted lines using Kepler's law, and what we are actually getting is something which is solid data point, whatever is shown here. This is x-axis in the center of the Milky Way, and this is the distance from the center of the Milky Way. It go up to 40,000 light year. If you go beyond stellar disk, because stellar disk finishes somewhere at 30,000 light years, you see there's nothing star, but still it appears there's a mass is getting contributed. Smaller size, anybody with plus level physics can be done. That means, but mass, whatever we require is something reasonably large. So this was the origin of something called dark matters. It was proved by using gravitational lensing also, because that gives independent proof. And right now we are in such a state that we have 4%, 23% dark matter, and dark energy is very large, something like 70% or so. that is it is something kind of anti-gravity kind of things. So now we have even gone much far ahead. We know our universe is expanding, and we have observational proof for that. A lot of observational proofs for that we know the universe is expanding. We can discuss that in details, but apart from this, is a cosmic microwave background which is everywhere. That means universe was hotter in the past. All these things has been done in extremely large detail. Nowadays, we know this cosmic microwave temperature with an accuracy of 1 part millions. And we can even understand what happened in the first few minutes when universe was born, what happened after 3 minutes, when structure formed, when star forms, all those kind of things. All these details are now known. For example, these are the kind of theory and model kind of prediction using cosmic microwave background. So it's not only like kind of approximation, so many things, so many orders. So now we are pretty sure we understand that how universe has been formed, right? But what I'm saying actually out of this, that then question arises that how universe might have been formed. So all these kind of things are going to be very, very important. And we are in a situation like where we understand that we are connected. We as a human beings are connected in the material body with such a huge number of stardust, dust, lot of supernova. So we should not feel alone. And we should feel proud also that we are able to think about such a vast universe, such a big universe, study them in such a detail. That's the beauty of our mind. That's the beauty of this mind as a faculty which we have, the consciousness which we have created. As a result, I think we should think broad, and we should not identify locally. We should identify globally. We should not, because of local identity is nothing. It's just like one dot, the solar system. The solar system, sun, which is the dominating solar system, is also not visible, even the Milky Way arms. So we should have a global identity. So I'm giving you here a kind of pictures. So Ritish and Priyag made a lot of my introduction, that where from I am, who I am. So I'm saying that we should have a global kind of identity. Okay. So let's give our address. This is going to be a collective address, so that we don't fight with one another for small petty things. We try to think about our existence. But the address which I have given here is lambda cold dark matter universe. That means there could be many universe, but your universe and our universe is one of the universe which we call lambda cold dark matter universe. Okay, this is a property. It has a 70% dark energy. It has 25% cold dark matter, and then 4 and 5% baronic matter, which we know through the baronic matter means whole periodic table and party of it is whatever we understand. And in this big universe, we have many clusters. Among that is a Virgo cluster, supercluster. And that is one of the thousands and millions of clusters. And around there, in that Virgo cluster, it has many, many local groups. So one of the local group is something in which we are linked. And in the local group, there are many, many galaxies. And among those galaxies, Milky Way is one of the galaxies. And in the Milky Way, there are so many stars, so many arms. So Orion arm is one of the things. And in this Orion arm, there is local stellar neighborhood. And in those neighborhoods, there is solar birth cluster. And then there is a solar system. And in that solar system, there is a planet Earth. And in planet Earth is all of us. So we should have the same address, same identity, everything same, religion, place. So we should invest more understanding this vastness and secretness and this mystery about the universe, and also the creator of the universe, so on and so forth. So we should have a cosmic identity. I hope this is relevant, especially in the era when people are fighting for small things. Thanks a lot. I will conclude here, but I would be very, very happy to take questions because I just covered. Thank you.
Thank you, Professor Hoomchand sir, for this wonderful talk. And I will be really happy to read or ask questions from audience.
Yeah, we can just simply talk. That will be wonderful. That will be wonderful. So, that's the main thing.
So within the audience, if someone wants to ask question, they can unmute the mic.
Yes, sir. I have a question.
Okay, go ahead.
Go ahead.
So as you taught us that the universe has a size and it is expanding. So as we know from our notion that everything should have an end. So what is that the universe is expanding into? That is the question.
Yeah. So this question come in many people mind, because what we think is like on a bigger container. So it's not expanding in some bigger containers. So that means then there's going to be bigger universe, right? So when I say universe is expanding, it's basically the space-time which is expanding. So when I say, for example, size of the universe, it's not the size of the universe what actually be. It's the basically size of the visible universe. Like, because light has a finite life travel time. So if I need to see something, I have a maximum time of the age of the universe. So whatever, then I can see now, till now, it needs some time for the distant object to reach me. But whatever I might, let's say I can have a distance of 10 billion light years away. So it's a visible universe. So there's nothing like it is universe is expanding on something. So it's basically space-time itself which is expanding. So when we say, for example, galaxies are moving away, so no galaxies are actually moving away. There may be local velocity because of attraction of nearby group or supercluster cluster. So actually, there is nobody's moving, right? So nobody is moving. It's the space-time which is moving. It's like somebody sitting on the chair or somebody is pulling the chair. Then people are fighting that one another person, you are moving away from me. A second say, no, you are moving away from me, just because of relative motion. It appears because that expanding of space-time, the effect it has on the light is exactly same what it would have been, because if there is real motion. We are not able to distinguish that. So this is about the mystery about expansion. So we should not think it like physical movement. It's expansion of space-time.
Okay, sir.
So there should be any kind of question is okay. I think you can ask any kind of question.
Sir,
I'll be happy. Yeah.
Sir,
Please.
Sir, what is the contribution of supernova for element formation?
Yes. So I told you about sun, right? Sun is not going to give you elements out, because sun, for example, sun-like star, as I told, the sun-like star, for example, sun-like star is going to give you at the most helium, and then they will move to their end stage. But it is the high mass star. I'm just going to show you here. It is the high mass star. High mass star, which are going to cook you a lot of stuffs. But cooking is not enough. But then somebody need to throw them out so that they come again and get mixed up in the diffuse medium. And that is the job which is done by supernova. Supernova means it's huge explosion. And indoor that explosion also shock waves form. And where you can have exothermic, endothermic reaction as well. Like you can even create lengthenite kind of element in the periodic tables. So if there is no supernova, there would not have any metals. Whatever metal, if at all, low mass star would have cooked, that will be would have been only helium, like sun would have done. So the high mass star, whose age is small, they explode, and when they explode, they also create shock waves, and many supernova explode. There's a lot of mixing, so it's the kind of recycling, and we happen to be the product of that recycled material, which contain all these matter. Otherwise, we wouldn't have metal on the earth at all. We would have only high helium would have been there, or hydrogen would have been here. Is it okay?
Thank you, sir.
Hello, sir. Homchan, sir. I'm Hemant.
Yes.
It's really
Sir.
illuminating talk, and we came to know about the information how Stardust and we are linked. My small question was that is there some limit that the star will end into limit of mass, that the star will end into black hole? What is that
Yes.
limit of mass?
Yeah. There is interesting physics behind it. In fact, that's what I was just telling, that astronomy and astrophysics is an area which has extremely large dynamic range in any physical parameter. You can take density, you can take temperature, you can take gravity. For example, density. We work on a density 10 to the power minus 4 particle per centimeter cubes. And we live right now, for example, here in the Earth atmosphere, 10 to the power 23 particle per centimeter cubes. And best vacuum we have is something 10 to the power 6 to the power 7 particle per centimeter cubes. Such an extreme range we have. Similarly, in mass, as you asked, there is a huge range, right? For example, when we do it very rigorously, like when star collapse, what happened that its potential energy increases, right? When its density increases, we call it compactness, m by r square. And some amount of its potential energy go into kinetic energy. So what does it mean? It means basically that temperature rise. When a star is something like that, then it need to relieve that energy so that more convection can happen. So that means you need to radiate. So that, and when you radiate, it heat up. If I talk about in terms of specific heat, it's a negative specific heat, right? Specific heat, you need to give energy to raise the temperature. Here in the case of star, you need to take away the energy, then temperature of the star rises. Negative specific heat. Nobody has thought about it, but it works. It happens. And then we also need to think then when temperature becomes very high, large, we have to take relativistic approach, whether we have to take non-relativistic approach. When we do statistical mechanics, when we compare kinetic energy with the potential energy, when we compare kinetic energy with the Fermi energy, for instance, so on and so forth. So it turned out that when I try to ask a question, if I give you a radius of a star, what is the mass it should have in stable hydrostatic equilibriums? It turned out that you can't have end product like stable structure if mass is more than 1.4 solar mass, which is supported by degenerate electron pressures. Okay, so what I'm saying that degeneracy of electron degeneracy pressure is not enough to support a star core whose mass is more than 1.4. This is the limit that for white dwarf. So you have not seen, or we have not seen any white dwarf which are actually supported by electron degeneracy pressure whose mass is more than 1.4. The next is that if mass is more than 1.4, then what happened? Then what happened that we can have endothermic reaction where proton and electron are mostly converted to neutron, and the neutron degeneracy pressure is more powerful than that of electron degeneracy pressure. So it turned out that for like up to 6, 7, 8 solar mass star, they can be supported by neutron degeneracy pressure. We call them neutron star. So they are very dense core. As I told, just to give an analogy, that if you take spoons of neutron star, so you need probably to lift them using JCVs, like tons of weights. And this range is because there could be magnetic field and number of things, a lot of things one need to go. It's really extremely exciting. We don't know even the equation of state of neutron star. What exactly the equation of state of neutron? How energy, pressure, and density are linked. So very exciting physics goes on. But if mass is even much more than that, that even neutron degeneration is not enough, then then nobody can't actually stop the crash of the star. Like star will be completely doomed. So we don't know what happened. Especially we don't know what happened beyond in the inner region where escape velocity becomes more than speed of light. In technical term, we call it event horizon. That inside it could be much more like a point-like object, or there could be some exotic thing happen. That we call black holes. So I have not touched all those things, just because, but it's really, really rich in physics.
Thank you, sir.
Every branch of physics. Yeah.
Yeah, Hemant sir.
Dr. Kulkarni sir.
First of all, let me apologize. My instrument was not working properly. I could attend only the last 30% of the class from 7:40 onwards. I would like to listen to the whole lecture once Hemant Kumarji sends me the whole video, and I'll comment. It was a great lecture that I attended, the 25 minutes, and it must have been a wonderful experience for the rest of you who were lucky enough to get the whole of the lecture. Thank you very much. And also, I would like to thank Professor Hemant Kumar for completing 8 sessions of this. It's 4 months, and it's a great achievement on his part as far as NASNI is concerned. Thank you very much. Thank you.
Thank you, sir. Thank you.
I have a question.
Yes, go ahead.
Hello, am I audible? Yes. So, sir, as since you said we have a cosmic identity, and we are living in one of the universe that is expanding. So, what will be the
Yes.
fate of such universe that is expanding? Like, I know that at this moment, expansion does not affect the galaxy because of its gravitationally bound system. But do you think that there will be a moment, there will be a time when the expansion takes over this gravitationally bound system? What will happen during that phase?
Yes. So great amount of work has been done in this one. Especially these are the burning questions which people want to know. In fact, nowadays there's in fact much more interesting thing, much more interesting tool which we have. That's called computer. We can simulate the universe in a computer. And although this simulation takes months and years of time on even a super computers, but it's all possible. Even we can try to see what's going to happen in future. But right now, it's very simple, basically. If we can measure the energy content of the universe, then we know whether this expansion of the universe is going to be expansion forever. It's something like that. If we throw a ball with speed more than escape velocity, that ball will go forward, it will never come back. Or whether we are just at the escape velocity, or whether we are smaller than escape velocity, then it will come back. So observation, in which $1 trillion has been spent, especially cosmic microwave background, for which WMAP and Planck satellite has gone into the space, suggests that we are somehow very close to a critical situation where we are going to end with like exact analogy which I have given with the escape velocity, right? We will just stay there. Neither we are going to come back as a crunch, neither we are going to keep expanding forever. So this means these are fine tunings. So everybody is puzzled that if I just go back, that how this fine tuning might have happened. If I try to see the fine tuning, what has happened today, and when I'm going to take the universe when it was extremely small, let's say of a size of Planck scale, like a 10 to the power minus 30 centimeters or something size, then this fine tuning turned out to be extremely large. Like it's not like 1 part per million, 1 part per billions, right? So nobody knows that who has done this fine tunings at that precision levels. But right now we are in a critical stage. We call that we are in a critical stage where universe is neither going to be closed, neither it's going to be open. Closed means it's going to be crunch, and neither it's going to be open. That's keep on expanding forever. It's going to be exactly at a critical level, which we call flat universe. It's a very interesting problem, but people has come up with some solution for that. In fact, Nobel Prize was also given. That's called inflation theory. So this is the situation right now, but observations are very tight, very accurate, very advanced. So we have no other way. We have to believe it.
Thank you, sir.
Thank you, sir. So I would also like to invite Professor P.K. Alwal.
Yes, somebody is asking question. Please let them ask.
Sure.
Good evening, sir. Sir, my question is from slide number 17. Sir, you have shown some elements. I think iron was there and hydrogen, helium, along with wavelength is also there. Sir, what are these elements representing in this graph? Like if we are observing light on the earth, these are the elements that
for example, these are this one. Let's suppose you can take this yellow disk as a sun, and whatever is outside is basically the gaseous, like atmosphere around the sun, right? Like earth has atmosphere, there's going to be gas content there. Now I'm saying that if they're cool, then we discuss that they are going to give, then they are going to take electron from lower state to the higher state. But when they take to the higher state, they come down very quickly, we know, but not toward you. They will be lost. They can go anywhere in the 4 pi solid angle. The probability that it will again come toward you is almost negligible. For you, it's a loss. So as a result, you will have this kind of dark lines in the spectrum. So that means these lines, as I told here, these are the fingerprint of the elements in the periodic tables. For example, if I take magnesium, magnesiums might have, let's say, doublet, as let's say 3s1 to 3p transition, which we call alkali doublets. These are the unique. If you take 2 lines of magnesium and take their ratio, it will never and never match with any of the other element because their atomic configuration is unique. So this means you can uniquely identify them. So these are the signature of that. So I'm saying that if you give me spectrum, I am going to identify them uniquely linked. These are calcium, ionized calcium. This is iron. This is let's say hydrogen line coming from n equal to 3 to n equal to 2, and so on and so forth. Sodium line, for example, here sodium doublet. Sodium lines, right? 3s1 to 3p transition. So it is telling me that material by which this atmosphere is formed has a heavy element. That means solar system was formed by a heavy element. But heavy element, I convince you, only can be formed in the core of the high mass star. Right? This means our material by which our solar system was formed is a recycled material. Right? Recycling means then material, whatever we have used in the earth, is a recycled material from thousands of supernova. And they may be spread over thousands of light years in the sky at the earlier time. So me, you, and everybody are linked with such a vast universe.
So, sir, here iron line is also showing up, but you just said that iron is present in relatively old stars. So does that mean
Not
that
only a heavy star, high mass star.
Okay, sir. Okay, sir. High mass stars.
Iron will be in the high mass star, right?
So in this solar spectra, is this iron element coming from sun itself or from the atmosphere environment between?
No, it's coming from the fuel by which solar system was formed. That is by which sun was formed. It's basically already there, right in the beginning.
Okay, sir. Okay, sir.
Nothing has been contributed by the sun. Whatever sun is contributing, it is just converting hydrogen into helium in the core. Even that will also not be liberated out because sun will not explode as a supernova. It will just become a red giant when it's going to engulf all the planets, and then it will become planetary. Then core will become white dwarf. So it is the recycled material from the supernova which has been exploded, and then the recycled material has given the second generation and third generation of star, like our solar system. So we are not made by the pristine material. That's what it means.
Okay,
our
sir,
body is linked with the supernovas.
Can I ask a question, sir? Hello?
Yes.
Am I audible?
Yes, yeah.
Very nice and very informative talk, sir. I just want to ask that which databases one can utilize for fetching the data which can be analyzed by the students and the faculty members, because a lot of data is available in many databases. So which one are you going to recommend for this?
So for example, if you want in general, the best data which is well archived, that's called Sloan Digital Sky Survey to start with. Why I'm saying it's best, reason for that is it's extremely well documented, and that data is free from the artifact which has been introduced by the instrument. All those has been removed out. So it's a kind of mine for you for number one thing. But then if you want specifically something, let's say you want infrared data, then there is another mission like WISE is there. WISC, Wide Infrared Survey. And there is something called Sloan Digital Sky Survey has huge amount of release. I think there is something like 18th release or 19th release right now. For example, I work star, you will have much abundant. I work on extragalactic active galactic nuclei having supermassive black holes. We also have something like 8 lakhs of them, which has supermassive black hole in the center. Now you can imagine that how many galaxy, how many stars you are going to see in this database. And it is extremely organized. Like data query, MySQL query, if you want to give, is like very well documented. A lot of things can be done. This is for optical, right? And you have some other question about any question about specific wavelength?
SDSS I have used for color graph. And what about the NED database? Because for extragalactic also is that data also very useful?
NED does documentation basically. But whoever has published data, they will just put it there. You just go by their names. You can search there. That's the only like they don't have their own collection. Whatever has been published, whatever they will just keep doing it for extragalactic sources. But if you want in high energy, then you should go to HESARC website. Okay. So it has taken data from HESARC. It has taken data from it's from all the space mission. It could be XMM by European. It could be Chandra by Americans, or it could be Suzaku by Japanese. It could be maybe 10 to 20 missions. For example, nowadays we have AstroSat. It's also being archived by ISRO. It will also be on that sometime. They have also their own archive. But integrated one is right now HESARC for high energy astrophysics. And WISE is extremely good for WISE and 2MASS for infrared astronomy. And then radio has its own one. That's completely another disease.
Okay. Thank you so much. Thanks a lot.
Sure.
Okay, so thank you everyone for your questions, and thank you, Professor Humchand, for your wonderful talk. Now, may I now request Professor P.K. Aluwalia, sir, the President of Indian Association of Physics Teacher, to kindly give the final remarks, and formally conclude the session.
Thank you, Ritesh. In fact, I was not present in whole of the lecture, but I had an advantage of listening to Professor Humchand in Dharamshala. And I think it was a kind of a recap in the end when I came back here. It was a wonderful lecture, and I really like the title of this, because where are we? I mean, in this whole of this universe. And sometimes, because we are thinking animals, this question keep on cropping to us that maybe from where we must have landed as stardust on our Earth itself. So that's a wonderful topic, and I think Professor Humchand has got a great communication skill to present everything in a very systematic fashion. And I will again watch it because I want to once again recollect it. Congratulations, NASNI coordinator and the honorable members of the NASNI group who are coming every Wednesday whenever there is a lecture, twice in a month, and participate in it. And now these lectures are available on the YouTube also. Professor Hemant makes sure that these lectures are available to us. Even if some people are missing, I'm sure that they are revisiting these lectures on the YouTube. And as Professor Arvind Kulkarni was saying, that this was the 8th lecture. I think 8 is a very interesting number also. We have crossed that kind of a limit. Hopefully, we are going to do great things. I just want to tell the participants here that Dr. Hemant was recently in Nagpur for a workshop on sky watching. And I saw the report of that and the enthusiasm which was there, which was done at the behest of regional, sub-regional council 08 Vidarbha. And they had roped in another organization, which is Professor Rajendra Singh Exploratorium in Nagpur. I think the idea of NASNI is spreading in the country. If you feel like having a kind of a workshop, I think you will not find a better person than Dr. Hemant for doing it for you. He has his own telescopes, and I hope I can take the liberty of telling you this also, that he is not just one person to come and help in the workshop. His wife is also a wonderful sky watcher, and she also conducts these workshops. So make best use of Professor Hemant for spreading the message of Nani. And I'm happy that at the end of each lecture, good questions are coming. There is one more resource person, Dr. Hemant, we can invite. There is one person, Mayank Wahi. You might have heard about him. And he gave a very interesting lecture the other day relating astronomy with the culture, and how the tribals used to look at the sky, and how the fishermen used to tell directions to the sailors, that take this wheel with you and keep this wheel in this particular direction, and you will find that you will reach there in so many days, a destination, while traveling in the sea itself. So there are wonderful things which can be shared with the group. Earlier, what we had done, we made an announcement that please give your number to make you member of the NANI, because we wanted only interested people to come. But I think we can keep on giving this call again and again, and we will try to do that very, very soon. So thank you, participants. Thank you very much. Thank you, Himanji, and thank you, Professor Humchan. Enjoyed.
Thank you, sir. Thank you, sir. Thank you.
And also, let me tell you that Professor Humchan has got a very dedicated team of his students with him, who also conduct workshops. In fact, in Himachal, they have got a project for what you may call as astro tourism, and they are establishing in different what you call dark skies of Himachal Pradesh telescopes, to invite people to come and enjoy the sky and watch the deep sky also. So these are some good news which I wanted to share with you. Once again, I thank each one of you for being here. Thank you. Thank you, Ritesh. Back to you.
Thank you, sir.
Thank you, sir. Thank you.
So I would like to thank P.K. Alwale, sir, and Professor Hemant Kumar, sir, for giving me this opportunity to host this session. And I hope in future I will get this opportunity. Thank you.
Thank you, Ritesh. Thank you very much.
Thank you. Bye-bye.
Thanks a lot.
Thank you, Homchand sir. Thank you very much.
Thank you, sir.